My topic is demystifying machine learning. So I want to show you a very simple machine learning application to show you what the big fuss is all about. So maybe first a bit about where I come from. So I work at Netguru, and that explains why I got so big of applause. So thanks for that. And I'm a senior developer. I do backend stuff, Rails. I do front end. I do JavaScript, CSS, basically everything. And recently, I've been doing some work on some of internal machine learning tools for our company. So what even is machine learning? Well, basically, it's a way of making some predictions about our data using data mining techniques. So you might have heard that the machine learning is on the rise, but basically it's just a rebranding of some ideas that were on the market for quite some time already. And my plan for this presentation is that after we're done, you should know one of the many machine learning algorithms and be able to understand what's the idea behind it. And then I will also show you why it's not as easy as I'm showing you it to be, because it never is, as you know. And at the very end, I will tell you what I think is the most important thing in every machine learning system. So everyone is on the same page. I'm just going to tell you briefly about what a machine learning system looks like. So at the very beginning, we have some data. And where does the data come from? It can come from many places. It can come from an Excel file. It can come from your database. Could be from Salesforce. You can collect it from, you could just take some data you collect already, like your sales records, for example, or you can gather those metrics specifically for the purpose of using them for machine learning. So the algorithm takes the data and builds some kind of a model that allows us to do some kind of predictions on the new data that comes in. So what could this model look like? So a simple model for determining if a milk is spoiled is to sniff it, and if it smells, just throw it away because it's a bad milk. And that's a very simple model, but it works. And yeah, so this algorithm gives us some kind of results, and it's usually in form of a prediction, so it can tell us whether the milk is spoiled or not. Or it can be a thing called regression. So based on historical data, we could try to estimate, for example, what's the revenue that the given client can give us. Okay, so there are also some other kinds of machine learning algorithms that do a little bit more than just simple predictions, but we're not going to talk about them, so I'll just leave them out. There's also another part of this system that I'm not showing on the slide, because I don't want to complicate it too much. So, because the predictions we make can change the way we work, because we can look at the predictions we made in the past, and if they are wrong for some reasons, we will have to adjust the things that we do with the data or the algorithm. But I'm not going to talk about this part either, but I just wanted you to know that it's also a part of a machine learning system. So every one of those three steps that I've shown you impacts the results in crucial ways. And what we want to do here is we want to build some kind of model that can give us accurate predictions based on the historical data, and we want to know what an analyst person would tell us about the specific case, but we don't have to include this analyst in this decision-making process, so we can process fast, large volumes of data. That's our goal. So I'm going to start with the middle part, the algorithm, because I wanted you to understand how it works and what it does before we go to the data and the results part. So what I'm going to show you is one of the simplest recommendation systems. Sorry. Okay. So we're going to look into a system that's called collaborative filtering, and it's a very simple idea, as you'll see in a moment, but it's used by many different companies like Amazon, Spotify, but also by companies like Netflix or Twitch or Twitter or Facebook or YouTube. Basically, many companies that can benefit from recommending their users something will use techniques like this one. So I just have to be clear, this is very simplified. I'm leaving a lot of things out, but this shouldn't impart your understanding of the idea. Okay, so the idea behind the collaborative filtering is if you have a friend and that friend has a similar taste in movies to yours, if that friend sees some new movie that you haven't seen yet and tells you that it was very great, the chances are high that you're gonna like this movie also. And that's pretty much all there is to it. That's the big idea. So there is going to be a little bit of numbers, but I tried to keep all the numbers under 5. So we'll see how it goes. Hey, so what you can see on the slide, in the upper left we have 4 movies and 4 people, and there are ratings by those people for every one of those 4 movies. And beside Mark, Paul, and Anna, we also have Judy, and we would like to find some movie recommendations for Judy. And as you can see, we also know what were the ratings that Judy gave to those 4 exact movies again. So what we would like to know is which people have similar tastes in movies to Judy. So what can we do? How can we find how similar they are? Well, let's maybe start with plotting this information. So we have Judy on the vertical axis, is it right? Yeah, and we have Mark on the horizontal, and we just plotted the movies. Mark gave gravity a 3, and Judy gave gravity a 2. So the gravity ended on a coordinates 3.2. So 3, 2, yeah. So we have this little cloud of points. It doesn't really look like a cloud, but yeah, I should have thought of that before I did this diagram. Yeah, so let's find a line that goes as close to every point in this cloud as possible. So there are algorithms that do that for us. We don't really have to do anything special here. There are tools that you will find for us this specific line, and you can do this in Excel. Everything I'm showing you can do in Excel. It doesn't need any fancy programming language to do that, really. And you can see there's this metric called R right next to it. And this is a statistical measure. Sorry for the big words, but it's describing how well this one line describes the cloud of data that we have on this chart. And this has positive value, which means, and that value is also very high, which means that the similarity between movie tastes of Judy and Mark are like, they are very similar to each other when it comes to their taste in movies. So for comparison, on the right side you have Judy and Paul, and we can see that the line goes down this time, and there's a minus in the R, so we're coming into negative values. And this means that they're not that similar, and they actually have exact opposite tastes to each other. So this R is called Pearson Correlation coefficient. I'm telling you this only if you want to Google it later, because you can find it on Wikipedia, which is where I stole this diagram from. Except for the arrows, I drew those myself. I mentioned those clouds of data, and actually those blue blobs look a little more like clouds now. So at the middle we have a round cloud, which tells us basically that there's no similarity between taste of those two people. Then when you go to the left, the number grows, and as you can see, the points start to fit more and more to the line. So when we go to the left, when we go to the positive values, yeah, I should have flipped that, didn't think of that. When we go to the left, along the green arrow, we're getting more similar results. When we're in the middle, there's no similarity at all. And when we go to the right, we're ending up with completely opposite tastes. Okay, so we calculated those values for Mark, Paul, and Anna, and we ended up with the similarity score. So what can we say looking at it? We only have 3 people, so I don't have to go into any deep analysis, but we can see already that Mark is most similar to Judy when it comes to their movie taste, and that Paul is least similar, and whatever Paul likes, Judy probably would hate. So, say? I don't know. I don't really know. Yeah, I'll leave that to those two to sort out their differences. Okay, so what can we do with the data that we just got with the similarity scores? So basically, we just want to say in which part tastes in movies of Judy are taken from Mark, and in which part from Anna, and in which part from Paul. But first, let's just see. We have 3 people. 2 of those have similar tastes to Judy, but there's Paul. And we don't really want to suggest anything that Paul likes to Judy, because she'll probably hate it, as we said. So we're only taking the top matches. And whenever you have a system like this, we'll probably just take maybe 20 or 30, it depends, the most similar people, and just leave out the rest. In this case, we only have 3 people, so we're gonna take 2 and leave Paul behind. And once we get all the people that we would like to use to build this formula for predicting if Judy would like a film or not, we have to scale them so their relative values stay the same, but they're sum up to 1. And you will see in a bit why we have to do it. Yeah, in a bit, meaning now. So we can say that the prediction for whether Judy would like a film or not is the first value, the 0.57, which we've taken from here, times Mark's rating, plus 0.43 for Anna, times Anna's rating. So if we have a movie like WALL-E, which Judy haven't seen yet, and we have all the values from other people, we can use this formula to calculate predicted value of Judy's rating, and it's actually quite high. It's 4.57. So what can we do with such value? We can say, hey Judy, there's a movie called WALL-E, which is most likely 91% your type. And yeah, that's pretty much it. This is like the whole idea about the collaborative filtering. And this is the basis for many recommendation systems. If you use FilmWeb, you can see if your friends have similar movie tastes to yours. And this number, this percentage, so is basically what I've shown you just now. And also Amazon uses the same methods to some extent. It's much, much more complicated, but it's still the same general idea. Okay, so this was how it works. And now we're going to talk about problems, which is always my favorite part. So the problem is if we're just starting, we don't really have much data that we could use to do those predictions. And the other thing is those data sets are usually very sparse. Well, Amazon has hundreds of millions of products and probably millions, or I don't even know how many, but I would say that there's definitely much more stuff to sell on Amazon than people that will buy it. And other problem is how to recommend new items that no one has yet rated in any way, because that's also a problem. Yeah, so this thing is called the cold start problem, if anyone wants to Google that after the presentation. Okay, so what are the possible solutions to this problem? Many applications will tell you that you have to select few categories or subscriptions in the beginning before you can do anything in the app. And I've only seen it on Twitch, but I've heard that now Netflix, Twitter, and Pinterest do the same thing as well. Yeah, new users can be recommended just the most popular items, and there will be no personalization in place. Or we can get the data from some other sources, like we can get it from Facebook. Or we can do something that, for example, Spotify does to some extent, which is using context-based recommendations. And in case of Spotify, they take songs and analyze them for features like, does it have a groovy bass line, or is it upbeat, or what's the tempo of the song? And they use these attributes to tell whether a song is similar to other songs, and they use that to make new recommendations. Another thing that you've probably seen on your Facebook feed is the clustering problem, or echo chambers. And the base idea is that if you started listening to folk, then you're probably only getting recommendations for folk bands on Spotify. So you listen to more folk bands, basically, and like the cycle continues. And you will never be shown anything that's not a folk band. And this slide illustrates the problem. This is data gathered in 2004, and it shows us links between political blocs in the United States. And those on the left, those blue blocs associated with liberals, and on the right we have the red from conservatives. And as you can see, there's not that many connections really between those two blobs, because they're really almost separate entities. And that's something that you can also see on your Facebook feed. And I remind you, this is from 2004, so this problem is not new. It existed for a long time. I think Facebook only made it more visible to us. Well, another problem is that people aren't very consistent in the ratings. Your taste in music changes with time. Also, you probably give out 10 much less frequently, 10 and 9, but the difference between 9 and 10 is the same as the distance between 6 and 7. So why should those differences in distance be treated the same? Well, for example, I have a friend who likes good movies, but he also likes bad movies. And when he and the thing is, when he rates a bad movie, he uses a scale between 1 to 10, and he tells me, yeah, I've seen this new movie by Uwe Boll, and I gave it a 7 on a scale of bad films, or bad movies. But that's the same scale that he uses to rate good movies, and just tells me, oh, this new movie from some new fancy director is great, it's like 7 on the scale of good movies. So he ends up with bad movies and good movies rated 7. So it doesn't seem very consistent, although I have to say, maybe it says more about his enjoyment of those movies, so maybe it's not that bad after all. Yeah, and also if you rate a movie right after seeing it, you will probably give it a different rating than if you wait and just do it on the next day. And also you can sometimes get influenced by what your friends are saying about that movie. If you go to FilmWeb that I've shown before, you can see what your friends said about a given movie before you get the chance to rate it. And this might influence your opinion as well. So these problems, the lack of consistency, these are not actually problems that have very good technical solutions, because you need to have someone who knows how people make choices, how people rate things, and that person is someone who, for example, specializes in cognitive sciences or in sociology or psychology. And that person is most likely not the developer. So these problems don't have technical solutions. The problem include trade-offs. And yeah, probably developer is not going to be the right person to call it. Okay, so we've been discussing algorithms so far, and let's just go we're 2/3 of the way through. If that calms you a little bit. Okay, so yeah, as I've written, I should have put all those things into the presenter notes. Yeah, don't read that. Don't read anything that's on the slides. You don't have to. I know because I wrote it. Yeah, self-deprecating humor always a thing. Yeah, so I lost my train of thought. Yeah, so why go again through data? Because we've been talking about data from the beginning. Well, there are some problems in the data that will always occur regardless of which kind of algorithm you use. So those problems I'm going to talk about now, they will show always, not only if you do some kind of recommendation things. Yeah. So your data can be biased because if your data set is a record of things that people do, every single decision that's in this data set was made by a human, and that human can have some biases, and that person might know about it or they might not know about it. But the thing is, it's still going to end up in the data set that we'll be using for learning. And for example, if the data set we're talking about is a record of decisions whether to give a loan to a specific person, we might find by analyzing it that, for example, single mothers are discriminated against in this data set. And how we can do that? We can, for example, take into account all the other attributes, like income or credit record, and leave out the one that says about being a single mother. If we see that the distribution or the decisions are skewed unfavorably for them, it means that there's some kind of bias at play. And when we're talking about algorithms that allow us to track back how the decision was made based on the data, well, we can sometimes correct those mistakes. But if the algorithm we use is more of a black box, then we have a problem, because we might not be able to track back to see what was the reasoning for a given decision. Yeah, so another thing is that your data will be inconsistent always. The part of the project of building those internal tools was collecting the data in the first place. And I found out that some of the projects have weekly sprints, some of those have bi-weekly. So how can I compare those two? Because they will have very different values when it comes to the number of points delivered or the points that we declared we will do and things like that. Well, the solution is to use some kind of relative metrics. For example, points delivered per week per developer, or number of bugs found per number of tickets in the whole sprint. But you have to know about it. We have to know. You have to make your data comparable between different data points. And yeah, sometimes tickets in Jira wander between states that we're not supposed to, and we didn't realize it at the beginning. And only later we realized that sometimes PMs will correct some mistakes, and that the ideal flow that we had in our head that we used to build the system that collected the information about transition projects, it didn't really work. It didn't even have the chance to work, so we had to rectify it as well. Yeah, and also you can see that sometimes you think a metric tells you one thing, but it really tells you another. And one example of that, you're measuring how much time it takes for a ticket to get from being in development to being done. And we thought we had it ready, but it turned out that part of the workflow we were measuring was client acceptance. And sometimes clients take a little longer than a sprint to confirm that, yes, this is what we wanted. So we ended up with a lot of sprints that weren't done on time, even though the development work was done. So what you have to do when you gather data, you have to look at the distribution of the data. You have to make some theories about the data and see if once you get the data, you can validate them if your theories are correct. And usually they won't be. Just putting it out there. Other thing, your data might be imbalanced. In our case, we have much fewer scenarios when it comes to the data we gather about projects where something went wrong in the project. So those few cases where something goes really wrong, they just missed in this whole amount of data that we gather. And actually, the cost of missing a potential problem in a project is much higher than just checking a few more projects for any ongoing problems. So you have to be aware that sometimes you have to assign a different weight to different scenarios. And you have to figure out a way to assign some kind of a cost to different kinds of decisions that the algorithm makes. And for that, you also need someone with a domain knowledge, some kind of expert. So if you gather data about projects, well, I just talked to some of the PMs, and it helped a lot. So we're nearing the end. So I'm just going to show you a little bit about the last part, which is the results. And I have a pretty diagram for you. This is similar to what I've shown you before. On the horizontal axis, we have a number of bugs reported. On the vertical, we have a number of QA tests that were being done for all tickets summarily. So obviously, as you can see from this diagram, if you wouldn't let QAs test so much, you wouldn't have that many bugs, which is the obvious conclusion you can have from looking at the data. Yeah, so just joking aside, the obvious interpretation is that because the QAs test, the more the QAs test, the more bugs they find. Does it sound about right to you? Does it make sense? No one's protesting, so I take it. Tough crowd. Yeah, but that's actually not what's going on here. What's going on here is because QAs found bugs in some of the tickets. Once the developer fixed the problem, they have to test them again. So that's the thing. It's the other way around. Because there are more bugs, the QAs have to test more. So you have to be worried that even though something might seem obvious to you at the first sight, you have to look deeper and always try to confirm your theories in some way. So, yeah, I hope this example showed you that the interpretation of your results is very important. I think I actually said everything that's on this slide, so yeah, that's great. Yep. And another thing about the results is, if your users know how you get those results, they can just game your system. And if there's any kind of incentive for them to do that, they will do it. And the best example I can show you is from an algorithm that you might not even think it's machine learning, and it's Google PageRank. And probably every one of you have heard about things like Google bombs, where you try to use dark SEO techniques to put some kind of connection between different, well, in this example, you might not see it from the end. So you're Googling for miserable failure and you get biography of President George W. Bush. So this is one example of Google bombing. And we also had a few of those cases in Poland as well, where phrases like liar would return you some specific politicians. And in one of those cases, it even went to court. So, yeah. And another example I have is I can't remember how long ago it was, but Microsoft put a bot on Twitter. It was named Tay, I believe. And it was supposed to learn from other Twitter users what to say, how to say it, like just try to keep up conversation based on what other users do. But unfortunately, many people were using Twitter to share some kind of profanities with this bot. So at the end of the day, that bot was also just shouting profanities on the whole feed. And that's just another example on how you can gamble some kind of machine learning data mining system. So, in summary, knowing what your problem is and what you're trying to solve, and knowing your data is crucial to your success. And machine learning is not something that's going to replace people, but it will help people to do things that were not possible before. And it won't really allow you to like full servers of servers. How do you call the places where servers live? What's the name for it? Server farms, yeah. 2 server farms full of servers will not really replace org of a single good expert. But they will definitely help those. And yeah, I promised before that I will tell you what's the most important thing in machine learning system building process. And this is a person, and that person is your domain expert. This is the person that knows your data, knows how it looks like in the real world, and has the domain knowledge to support you in your role as a developer. And you have to support that person as well. And that's all I have for you. Thanks. And I also would like to thank Bartek, Magda, and Kuba for giving me some feedback on a very early version of this talk.
All right, so that's all. So, do you have any questions to Chris?
When you've been talking about that collecting data, when the people are going horizontal in their opinion and they stay in that site.
Which part of the talk?
There was a big red and blue.
Oh yeah, okay. Yep, this is it.
So, do you think it's how much impact it has on the world when the main services start to using that system? When they're going to separate these people like natural, because all people in the world using internet and searches stuff, so internet is naturally separating people, like, in your opinion.
Well, as I mentioned, this data set is from 2004, so this is something ongoing, and my guess is that what happens on Facebook is it just mimics how we behave in world as well. Like, I don't think I have that many friends that I interact on a regular basis that I disagree strongly on politics. So, in my opinion, the separation of people on Facebook feeds just follows what we do in real life.
So, I have a question, Chris. From your point of view, from your perspective, how much of math you or one should understand to basically take advantage of using machine learning, assuming that he or she has a domain knowledge or knows somebody who knows it? How much of math do we need to clearly understand?
So you don't really need math. You actually need statistics more. You don't ever have to do calculations manually. You can usually do that with Excel or some programming languages, but you need to understand what those functions, those statistical functions show you about the data. You have to be able to interpret the results. So you don't really need maths, but you need the statistics.
you. The movie example you shown shows that the problem can be easily solved with the correlation. So you just one can need only the regression analysis to solve the problem. So why use neural network if you can use the correlation analysis or supported vector machines?
Because this is an example and I wanted to make it simple. And I wasn't really sure if I haven't gone too far, because I could probably figure out some easier way to do the comparison. But this is the one you will find in literature, so I just went with it, because I didn't want to invent anything new and make you more confused when you try to Google something more about it.
So what are the real problems we solve in that group?
What you mean?
What kind of problems you solve every day? So the question is, what kind of problems you solve with the machine learning in Netguru?
So this is actually an ongoing effort. I mostly talked about, I used examples only for the data collection when I was talking about and some of the results, but right now we're just collecting data and trying to figure out the best way to use it. And I found that just collecting the data and trying to understand what it represents makes you much more aware of what's going on in the project. Well, currently we gather some kind of KPIs about the project, and we put them on Salesforce, so PMs have some kind of approximation of what was going on the last sprint. But I believe that one day it will be possible for us to detect some problems that are happening in the project much quicker than we do it now.
Give a round of applause for Krzysztof.